In Chapter 5, Section 4, we move on to graphing our trig functions. Now, the pattern of transformation of functions that you learned in college algebra is directly applicable to the pattern of transformations that we're going to use with trig. Let's do just a quick review of that pattern of transformations. In college algebra, when we were transforming a function, for example, we're just going to use our quadratic function, our squared function. Our pattern of transformations looks like this, where you had positive or negative a, you had a function, in this case I've done squared, it could have been square root or cubed or whatever, x minus h, where this h is my horizontal shift attached to the x, so that's my horizontal shift. And then we had this plus k added on at the end. It could have been at the beginning. That would be our vertical shift. And I always taught in my classes h is for horizontal and then k is the other one. The vertical is the other one. A was my vertical stretch or shrink, depending on whether it was a whole number or a fraction. You had a negative here that would reflect it across the x-axis. If a negative showed up here, it would reflect across the y-axis. But this was your general pattern of transformations. In trig, looks very, very similar. We just use different variables. Our pattern of transformation of functions, when we're graphing trig functions, we're still going to use a here, except a is typically going to be our amplitude. Now I'm going to use sine as my function. I could just as easily have done cosine omega, and then in parentheses I have x minus phi, and then I have plus beta. Now for this transformation of my trig functions, a is going to be typically my amplitude. It's how high and low I go from center. Omega is going to be an adjustment to the period of my function, where period for sine and cosine is 2 pi divided by omega. If it were tangent or cotangent, it would just be pi divided by omega. Phi represents what we're going to call our phase shift, where our function shifts to the left or right, still horizontal shift attached to the x-axis. And plus or minus b, beta, gives us our center, which is our vertical shift, either up or down from where we expect to start at the x-axis. Now this amplitude, this a out here, is really the absolute value of a. If I have a negative, that does cause a reflection. That negative here would still be a reflection over the x-axis. Okay, so this a is this amplitude is my vertical stretch or shrink. Period is the same thing as a horizontal stretch or shrink. And we didn't deal much with a horizontal stretch or shrink with college algebra. We typically stuck with that vertical stretch or shrink idea. Okay, so write this down maybe on a post-it note where you can keep it handy for you to look at as we go through the next couple of sections for graphing. Let's go back to our notes. All right. To graph a function quickly, a graphing calculator can be used. You know what you guys are not allowed to use in this course? A graphing calculator. So I don't want you to depend on a graphing calculator. I want you to understand how to do it yourself based on transformations of functions, not based on calculating a ton of points. Because these functions are periodic, once you know the shape, you can just keep repeating that over the right period. Sine and cosine are almost identical. One is a phase shift, pi half from the other. The independent variable x represents the angle. It's using x for your angle instead of theta or t or something else. Y is the dependent variable, and that is going to be the y coordinate on the unit circle. Now, one thing you need to be aware of, As we start graphing trig functions, we are stepping away from the unit circle. Our rules that we start with apply directly to the unit circle, but once we step away, once we change the amplitude or have a phase shift or change the period, we have taken it off of the unit circle and we can't map it back onto that. All right, graphing sine function. We're going to complete this table and then plot the points to create the graph of y equals sine x. In addition, while you're working, ask yourself why a table going from 0 to 2 pi was picked. Well, why do you think? Our period for our sine function and cosine is going to be 2 pi. Sine, cosine, and their reciprocals, the period is 2 pi. Tangent and cotangent are periodic over pi. What this is telling you is that the domain is my function, the domain is my angle that I'm interested, and the range is the function value. For sine and cosine, I can find any sine function value, cosine function value for any angle. So my domain is going to be all real numbers. My range is going to be limited to, on the unit circle, -1 to 1. As I do some transformations, that's going to change, however. Now, we aren't going to do every angle. We're going to focus on our quadrantal angles. So I'm going to go through here and I'm going to say, you know what? I'm not going to worry about the pi sixths. I am going to totally focus on 1, 2, 3, 4, 5 major points representing my quadrantal angles as I move a full rotation around my circle. So I have 0, pi half, 0, pi half, pi, 3 pi halves, 2 pi. That's my 5 angles, 1, 2, 3, 4. And notice that I do a full circle. I come back to my starting place as far as the y coordinate goes. All right, so at 0 degrees or 0 radians, y equals sine of 0. The sine function value is 0. So at 0 degrees, sine is 0. At pi half, sine is 1. At pi, sine is 0. At 3 pi halves, sine is -1. And come back around to 2 pi, sine is 0. So those are the plots the points I'm going to plot. 0, 0, pi half 1, pi 0, 3 pi half -1, and 2 pi 0. So you'll notice that here is my x-axis, here is my y-axis. My y-axis is numbered using the radian values. X-axis is numbered using integers. And let's plot our points for our graph. Sine starts at center at 0, 0. This is my parent sine function. Sine starts at center, it goes to its peak at 1, comes back to center, goes down to the trough, comes back to center, and that is one cycle, one period of the sine function. This sine function is going to continue forever to the left and to the right, modulating from center, peak, center, trough, center. Now it hits every point in between. It's a nice smooth curve. Do not graph angles for me. Graph nice smooth curves. For my sine function, y equals sine of x, my parent sine function, the domain is all real numbers. So from -infinity to +infinity. The range are those values between -1 and 1 as long as I haven't done a transformation that stretches this vertically and changes the amplitude. The sine function is an odd function. We learned that in the last section. As symmetry of the graph with respect to the origin indicates. If I kept going back this way, I would go down and then back up, and I would have that twist in the middle around the origin. The sine function is periodic over a period of 2 pi, unless I had change omega and have a horizontal stretch or shrink that changes the period, but the parent sine function is periodic over 2 pi. The x-intercepts are at the full values of pi. So I see I have an x-intercept at 0, at pi, at 2 pi. I would have another one over here at 3 pi, one back over here at -pi, etc., etc. The y-intercept is also at 0. sine function starts at center. The max function value is 1, and it occurs at the pi half. The minimum is at -1, and it occurs at 3 pi halves. And those would just keep going. If I kept going, I would hit another maximum right here at 5 pi halves, another minimum down here at 7 pi halves. Because that sine function is periodic, it just goes on forever unless I choose to restrict it. Okay, let's talk about some transformations. Just a reminder, y equals a for amplitude. Sine omega is going to be my period change, x minus phi plus beta, where this gives me a shift of center. This gives me a horizontal stretch or shrink for the period, because period is 2 pi over omega. This is my amplitude. And phi is my phase shift, horizontal shift left to right. Okay, let's do this one. Y equals a -2 sine of x plus pi fourth by first describing the pieces. Well, what is the function we're graphing? We're graphing a sine wave. There's my function, sine. What 3 transformations are happening, and what is that going to do to my function? The first transformation we're going to talk about is this negative out front. That negative out front is going to reflect it over the x-axis. So that last sine function started at center and went down. If we reflect that over, we're going to start at the center and go up. The second transformation that we see is that 2 here, that amplitude change. That's a vertical stretch by a factor of 2. So now my range is going to be from -2 to +2 instead of -1 to +1. And finally, we have a phase shift here. This pi fourth, remember it starts as x minus phi. This is x plus. So this is going to be a phase shift to the left because I had to have plugged in a negative pi fourth. Now, one thing that I want to make us aware of, we are going to skip this while we graph because this is our very first real graph. So I recognize that this would be a phase shift it back to the left, but I'm not going to do that right this second because I want to get down the basics. Okay, so think about our last graph. We started at center. Let me pull that back out. We started at center. We went peak, center, trough, center. This time, we're still going to start at center, but it's going to be reflected. So instead of center to peak, we're going to go center to trough. And my peak and trough aren't going to be at 1. My amplitude has been extended to 2. So I did not change my, I didn't change my major points where they're going to fall. I'm going from 0 to 2 pi, starting at center. I'm going to go down to the trough, which is at -2 because my amplitude is 2 now. Then I come back to center, peak, center. There's my 1, 2, 3, 4, 5 major points. If I wanted to do another cycle, I could do that. What if we took this and we shifted it to the left? Pi fourth. What would that look like if we went ahead and did this phase shift? Well, if we did that phase shift, this first point wouldn't be at 0 on my x-axis. It would be at pi fourth. I would shift it to the left, pi fourth. So this would be the same sine function graph with the phase shift. So this is no phase shift, and this is with the phase shift. You see what that phase shift does. My amplitude change was a vertical stretch. It went up and down to 2 instead of just to 1. My phase shift shifted me back to the left. Why did I go to the left? Well, because my pattern of transformation starts as x minus phi. Here I have x plus pi fourth, which means it had to have been x minus a negative pi fourth. So my phase shift is a negative pi fourth to the left. All right, let's switch and do cosine. Cosine looks just like sine that has been shifted by pi half. So my cosine function, cosine is a sine wave shifted either right or left, depending on how you want to think about it, pi half. So where sine starts at center, cosine is going to start at peak. We're going to start at the peak, okay? We're going to start at the peak with our graph. So once again, I'm only interested in my 5 major points. Now, I graph things a little bit differently than my math lab, so when you do this, show me an example or help me solve this in my math lab, they may give you steps a little bit differently. That's fine. There's more than one way to do this. I think my way is the simplest, or I wouldn't show you my way, obviously, but you can do it however you want. All right, at cosine, let's think about our circle again. If I were on my unit circle and I'm traveling starting at 0, pi half, pi, 3 pi half, and then back to 2 pi. What is my cosine function here? Well, it's 1. So that point is 0, 1. When I rotate up to pi half, my cosine value now is 0. Over here, cosine function value is -1, goes back to 0, and then back to 1. So my ordered pairs that I'm going to graph look like this. All right, so let's graph this cosine function. Again, I have numbered my x-axis using the angles and radians and my y-axis using integers for my function value. I start at 0 radians. My cosine function value is 1, so I'm starting at peak. At pi half radians, my cosine function value is 0, so I'm at center. Then I go to -1, that's trough, back to center, and then back up to peak. This is just one cycle, one period. It needs to be a nice curve, look like just kind of a different, we cut our sine curve at a different piece. Instead of going from center through trough and peak and back to center, I've gone from peak to peak. Another way to graph one cycle would be to go from trough to trough. This is one cycle of my cosine function. All right, we ran out of space on this page to list the properties of cosine. So let's kind of pull up the next page to do those. The domain of cosine function is all real numbers, just like the domain of sine function, all real numbers. I can write that -infinity to +infinity. The range is limited again by the amplitude. Parent function is from -1 to 1 unless I have a vertical stretch with an amplitude change. Cosine function is an even function. Remember, cosine and its reciprocal are our only 2 even functions, as the symmetry of the graph is symmetric with respect to the y-axis. The cosine function is periodic with a period over 2 pi unless I have a value for omega that has a horizontal stretch or shrink, but my parent function is periodic over 2 pi. The x-intercepts fall at those pi half values. You can see where I hit the x-axis. That's unless I have a phase shift. And the y-intercept is at 1. I start at peak. The max value is 1, and it occurs at x equals 0. The minimum value is -1, and it occurs at x equals pi. and then it's periodic, so those are going to be repetitive, just like with our sine function. Okay, let's do another cosine function graph. We have y equals cosine of 2x minus 3. Okay, so what are we doing with this y equals cosine of 2x minus 3? Well, we're graphing cosine. And so something we know about cosine is that as long as it's positive, it starts at the peak, not at center. What are the transformations we're applying? Well, we have this value of 2 attached to the x. That is our omega value. So omega is 2, which means we are changing the period. Our period starts at 2 pi divided by omega, so we've got 2 pi over 2. The period is just pi, so we've done a horizontal shrink. We're going to complete an entire period in pi radians instead of 2 pi radians. It's our first transformation. Our second transformation is this value for beta down here at the end. Beta is -3. That shifts center. So we have a vertical shift down 3 units. So my center is not on the x-axis. My center is down 3. That's the very first thing I'm going to mark on my graph. My center is not here at the x-axis. My center is down here. That's going to hopefully help me remember where I'm going. Now, did my amplitude change? Well, amplitude would show up here in front of cosine, and it didn't. So amplitude is just 1. So from center, I'm going to go up 1 and I'm going to go down 1, which means my range is from -4 to -2 for this function. I'm going to graph my 5 major points, and those 5 major points are going to go from 0 to pi. So I need to think about where those points are going to fall. I need 5 points, gives me 4 intervals. So I take my period always and divide it by 4 to find out how far apart those points are. So my interval size is pi/4. My first point will be at 0, and then 1 pi/4, 2 pi/4, 3 pi/4, 4 pi/4, 1, 2, 3, 4, 5. There's my 5 points. So if I simplify this, I have 0, pi/4, pi/2, 3 pi/4, and pi. That's where on the x-axis one cycle will fall, from 0 to pi. So 0, 1 pi/4, make sure you mark your x-axis correctly. Pi/2, 3 pi/4, and pi. That's one cycle. Cosine starts at peak. Peak is going to be -2 because center shifted down. So peak, center, trough, center, back to peak. I completed a single cycle over one period, pi radians. If I wanted to do a second cycle, I could go from pi to 2 pi, or I could go backwards to -pi. If I wanted to do a second cycle, I could say, okay, well, I could go -pi/4, -pi/2, -3 pi/4. There's -pi. This is at peak. That would be center, trough, center, peak. And there is a second cycle. One cycle. And then there is a second cycle. One cycle. If it asks me to do more than one cycle of that function. Okay, excellent. Let's look at sinusoidal functions for exploration number 3 and see what it has us doing. As defined in many dictionaries, sinusoidal functions are of relating to, shaped like, or varying according to a sine curve. This means that any curve that is a transformation of the sine curve is called a sinusoidal function, whether it's sine or cosine. Cosine fits that definition. So we're going to take our basic parent function graph, y equals cosine x, and shift it to the right pi halves units. So if I took cosine equals y equals cosine x, let's do that in blue. Y equals cosine x. Cosine is periodic over 2 pi. So I would start at peak because cosine starts at peak. This is 1 cycle of cosine. And then if I shift so that I do y equals cosine of x minus 2 pi, or pi half, that shifts me to the right pi half. My peak is going to start here. So that moves me here. And if I worked it backwards, I would see that I would hit center. And what I end up with, cosine of x minus pi half, is the same thing as the parent function sine x, because that's how they're related. Cosine is just a phase shift pi half away from sine function. Okay. The next thing we're going to do on our next exploration is we're going to compare some changes in our graphs. Now, to make this happen, you should have, let me see if I can find mine. I grabbed a sheet of paper and now I can't find my sheet of paper I grabbed. Sorry guys, I'm looking for, here's my graph paper. Okay, you should have printed off a sheet of graph paper. If you didn't, you can just use another sheet of paper, but it's really kind of important to have these exact graphs available to you to compare. Okay, so we're going to start with this number 1. Sine and cosine functions are transformations of each other. The sine and cosine functions called sinusoidal functions. Let's explore some generalities. So we're going to look at some general transformations. If we compare f of x is sine of x, g of x is 2 sine of x, and h of x is 1/2 sine of x. This value out in front that we're playing with here is a. In general, the values of y equals a sine of x and y equals a cosine of x, where a is not 0, always satisfies the inequality from negative a to positive a, and again from negative a to positive a for both sine and cosine. The absolute value of a is our amplitude. It tells us how high and how low our graph goes. It dictates, again, the height of the graph, the peak and the trough. In terms of transformations, it determines the vertical stretch or compression, stretch or shrink. Why do you think the amplitude is the absolute value of a? Because we don't care about whether it's positive or negative. It tells you how far from center. Distance. It tells you how far from center. So sine of x, my range we know is going to go from -1 to 1. So let's graph that first. So this is our exploration for 1, right here, exploration for 1 graph. Sine of x goes from 0 to 2 pi. Let's just graph it using the grids as marks. So this is going to be 0, pi half, pi, 3 pi half, 2 pi, and then our y-axis we will just count by ones. Sine starts at center, so f of x is going to be center, peak, center, trough, center. That is 1 cycle of y equals sine x. F of x equals sine x. My amplitude is 1, so my range is from 1 to -1. All right, let's do the next one. I'll do it in green. G of x. Y equals 2 sine x. So I'm going to take this and I'm going to stretch it by a factor of 2. So now my range is going to go from -2 to 2. I still start at center, but now I go up twice as far and down twice as far, so that I see I hit the same center points, but I have a vertical stretch. And then finally, h of x, a is 1/2. Right here, a is 2, and right here, A is just 1. A is 1/2, so my amplitude is 1/2, and my range has shrunk to -1/2 to +1/2. So I'm only going to go up and down a 1/2 unit from center. So it is a vertical shrink. I've made it much flatter. All right, that's how that value A, amplitude, affects our graph. Now let's look at number 2. And this is where we're going to graph exploration for number 2 on this next grid. Compare the table below by looking at the graph of the following functions. So we've got f of x equals sine x, we've got sine 4x, and we've got sine 1/4 x. So we have different values for omega. Now f of x equals sine x is periodic over 2 pi. Well, 2 pi over omega. Omega is just 1 here. It's just 1x. So it's periodic over 2 pi. So let's sketch that parent function one more time for sine. This is pi. This is 2 pi. So center, peak, center, trough, back to center. Sine function starts at center, goes up, goes down, comes back to center. That's f of x. Then I have g of x. Here, omega is 4. So sine is periodic over 2 pi divided by omega. 2 pi divided by 4 gives me a period of pi half. So I've got to do this whole cycle in pi half. Wow. So I'm going to take, so if my period equals pi half, I've got to divide that by 4 times 1/4. So I'm going to count by pi eighths to get my points in. So, wowee, that gets really smushed together because pi half is right here. I've got to do the whole cycle from there to here. So I'm going to go up, down, and back from 0 to pi half. My points are going to fall at 0, pi 8, 2 pi 8 is pi 4, 3 pi 8, and then 4 pi 8 is pi half. Those are my 5 major points where they fall on the x-axis for g of x. And then my final one is a horizontal stretch. Here, the value for omega is 1/4. So when I start at 2 pi divided by omega, that's 2 pi divided by 1/4, which becomes 2 pi times 4, which means I have stretched out one period to 8 pi. All right, so here is pi, 2 pi. This would be 3 pi, 4 pi. Oh my. I don't even know if it really was going to fit here. We're going to try if we can get to 8 pi, 5 pi, 6 pi, 7 pi. This doesn't fall out very well, but we're going to try it. So if my period is 8 pi, if I divide that by 4, I have a point every 2 pi. So I have points at 0, 2 pi, 4 pi, 6 pi, and 8 pi. 1, 2, 3, 4, 5. There's my 5 points. So 0 at center, peak is at 2 pi, center is at 4 pi, trough is at 6 pi, and then center is at 8 pi. So I take my graph and I, whoops. 2 pi, 3 pi, 4 pi, and then it got distorted here at the end because I ran out of space on my paper. But you see how it just really, oh, and I went up too high. Oh my goodness, guys. That should have only gone up 1 to right there and only down 1. So this should have been much flatter. I wish I had, I don't have any whiteout. This does not go up that high. This should flatten out at 1 because my amplitude is just 1. My points are here. So in general, the value of the functions, y equals sine of x of omega x and cosine of omega x, where a is greater than 0 as long as my amplitude is not 0. I have a period for sine and cosine of 2 pi divided by omega. Represents how long it takes to draw a cycle. It's my horizontal stretch or shrink. Okay, so here's my theorem. If omega is greater than 0, the amplitude and the period of my function, sine or cosine, amplitude is that absolute value of a, and the period, or t, is equal to 2 pi divided by omega. That just reiterates, gets you in a definition box what we have been talking about doing. So for 3, we're just going to practice our knowledge base. Identify the amplitude and period of these given functions. Well, amplitude is out front, period is attached to the x. My amplitude here is 4, not negative 4. That's how far up or down we go from center. The period is given to us by, period or t, is given to us by 2 pi over omega, and here omega is 3. Let's look at the next one. My amplitude here is, before we do that, we've got to deal with this negative argument. We do not leave that argument negative. Is sine odd or even? Well, cosine is my only even function, so sine is going to be odd, which means I end up with, therefore, I end up with y equals negative 1/2 sine of pi x. So a is a half. Remember, absolute value. That negative means I'm going to reflect it. If I were going to graph sine, I would go from center to trough instead of center to peak. A is 1/2. T period is 2 pi over omega. 2 pi over omega here is pi. So my period just comes out to be 2. This means when I number my x-axis, I'm not going to number it using pi. I would just number 1 or 2, 3, 4, depending on how many periods I need. Okay, now because remember I told you I graph things a little differently than the book does, we're totally going to skip this top. We're going to skip through here. We are not going to divide graphs into subintervals. That's unnecessary roughness. We can get by with doing it a little bit differently, and I think that it works better. Okay, steps for graphing a sinusoidal function in the form of a sine omega x or a cosine omega x using key points. The very first thing you're going to do is determine the amplitude and period. After you've done that, you're going to divide that period into 4 equal intervals. Into 4 equal intervals. Remember, my period is t, so you're going to do t divided by 4, literally, divide it by 4. After you do that, you obtain your 5 key points. Those intervals tell you where those 5 key points fall. Amplitude tells you how high up and down you go. Whether it is sine or cosine tells you if you start at center or at peak. And then you just plot your graph. All right. Let's do a couple of these. So for this first one, we have y equals 4 sine of 2x. Well, my amplitude is this 4. My period, t, is going to be 2 pi omega, where omega is 2, so my period is just pi. Now, I'm not going to do this for subinterval mess, but I am going to find my interval size to find my 5 key points. My interval size, I take t, my period, and I divide it by 4. So I'm going to hit a key point every pi fourth. I don't have a phase shift, so I'm going to start at 0. 1 pi fourth, 2 pi fourths is pi half, 3 pi fourths, and 4 pi fourths is pi. There's my 5 points. Now, because my amplitude is 4, the range of my function is going to be from -4 to +4. I don't have a center shift, so I don't need to worry about moving it away from center. My 5 key points. Sine starts at center, so I'm going to have 0, 0. Then I will go to pi4, and sine goes up as long as it's positive. So pi4 is going to go up to 4. Pi half, I will come back to center. 3 pi4, I'm going to go down to trough. And at pi, I will be back to center. So those are the 5 key points that will go on my graph. All right, there's my graph. My x-axis needs to go from 0 to pi. I did it probably way too long. I'm going to divide that into 4 equal intervals. So there's pi1/2, pi4, 3 pi4. My y-axis needs to go 1, 2, 3, 4. 1, 2, 3, 4, because that's my amplitude. And then I graph. Sine starts at center, and then it goes to peak. Back to center, down to trough, back to center, and there is 1 cycle of my graph. If I wanted to, I could just keep going for another cycle if I were asked for a second cycle, or I could go back to the left and do a cycle that way. Okay, let's look at our next page. Sorry, guys. And I think we're going to pull back our extra graph paper for this one because it says graph here, but it doesn't really give me enough room. So we're going to do our work here, and then we're going to graph on one of our empty graphs on our extra graph page. So I am asked to graph -5 cosine of -pi1/2 x. Now, cosine is an even function. Cosine is even. So this is the same thing as graphing -5 cosine of pi1/2 x. So my amplitude is 5, but I need to remember that I'm going to reflect it across the x-axis because of that negative out in front. Not doing subintervals. My period t is 2 pi divided by omega. Here omega is pi1/2, which means I have 2 pi times 2 over pi, which gives me a period of 4. So where are my 5 key points? Well, 4 divided by 4 is just 1. So I'm just counting 0, 1, 2, 3, 4, right? So I've got 0 something, 1 something, 2, 3, and then 4 as my x-axis coordinates. Now what about y? I don't have a center shift, so I'm going up and down from center. I'm graphing cosine, usually starts at peak, but we reflect it. So it's going to start at trough. Where is trough? -5. Then I go to center, peak, center, back to trough. Okay, we've got that information. Let's graph it on one of our extra grids. Let me see if I can get these points on here. Upside down is fine, right? So this is example 5. So 1, 2, 3, 4, 5 here. 1, 2, 3, 4, -5 here. And I can just count 1, 2, 3, 4. 0, 1, 2, 3, 4 on the x-axis. All right, let's graph. Cosine starts at peak, except this is negative cosine, so it starts at trough, center, peak, center, trough. Oh, it got stretched horizontally in a serious way. Or, yeah, vertically. It got stretched vertically in a serious way, didn't it? So that's what my graph for example 5 looks like. Awesome. Okay, let's look at the next one. If. Here's an if. On both those last examples, 4 and 5, if +2 were tacked on at the end of the function or at the beginning, what would that do to the graph? Well, that +2 would be a value for beta, which gives me my center. So my center would shift up 2 units. which is going to change. It's not balanced on the x-axis anymore. It would be balanced around 2, so it would change the range of my graph. And then this last example says to find an equation for the graph below. Now we're going to do the most simple equation we can. If we assume there's no phase shift, here's my y-axis right here. So here's my y-axis, and I see that peak and trough are 3, so A is 3. I'm starting not at center, I'm starting at trough. So this is going to be a negative cosine graph. The simplest version of my equation will be for a negative cosine function graph. What is the period, one cycle? If I go trough through center to peak back to trough, so from here to here is one cycle, my period is 8. T is 8. Well, I get to T is 8 by starting with 2 pi over omega. If that equals 8 over 1, I can solve for omega. That, if I solve it like a proportion, I get 8 omega equals 2 pi, or omega equals pi fourth. So this is all of the information I need to say that my function would be y equals negative 3, because it's reflected, amplitude of 3, cosine of, and then omega is pi fourth, omega x. That is the equation of that graph.